First part of it is what they call the monitor. The monitor contains the power routine. The monitor contains the keyboard layout so that it knows when you press the key that you're pressing a certain row and column, and that really is an A or a capital A or a lowercase a. It knows shift key. Then in Grom chips 1 and 2 is just the basic language. That's the basic interpreter. It's what converts what you've typed in. It's been saved into VDP memory for basic, and it converts it into tokenized code. It executes it. And in this Grom chip 1 is the error messages, and part of the basic interpreter. And Grom chip 2 is the balance of the basic interpreter. The cartridge Grom is whenever you plug a cartridge into the front of the port, if it just has Grom in it, then it's contains some number of chips of Grom here, and it can contain up to 5 Grom chips in it, or 30K of Grom. Now what TI did that is very special is they put the routines in the machine to talk to more than one cartridge at a time. We can have 16 cartridges online. That's 16 times 30, or 480K of Grom code online, plus the 18K of Grom that's in the console. So that's 498K of Grom code. Why they advertise this thing as a 16K machine, I'll never know. With those modules plugged in, BASIC can access all the calls in those modules. So if you had a Miniman plugged in, and you had an editor assembler, and you had the PRK plugged in, you could write a basic program then that could do the call Ds from the PRK. You could do the peek B and poke Bs in the editor assembler, and you could use the old EXP MEM2 in the Miniman. And they're all available to your power. So with 16 modules out there with calls in them, that's a lot of memory for your basic language to access. In other words, you're just building a subprogram library or subroutine library by adding more and more Grom cartridges. Unfortunately, it takes a little bit of special hardware, which TI never released, in order to plug 16 modules in at once. And we're looking into it. I'm not making any promises. I don't know when or anything else at this time, costs or anything. We're just looking at it right now. But the council and the languages will support it. We've looked at both basic and extended basic, and they will support a Grom library. Every now and then, you may have seen, maybe when your computer locked up, you switched modules at one time and it didn't come back to the title screen properly. You may have seen a little message come up, review module library. And it would be, let's say that you had a module plugged in, so maybe it was number 4 on the list, but you pressed it and nothing happens. Maybe you pressed it, generally you just go back to a title screen at that time. And that review module library was put there for when you had a Grom library box with 16 modules out there. And that's what that's for. And it will go then through and scan those modules and tell you what's out there. And from there you can make another selection. So, hasn't been tested, but it looks like it's there software-wise. It looks like it's there. So, the last memory map device is VDP RAM, and that's the 16K that TI touted this machine as being, and that resides also in the console. And it is talked to through a VDP processor we call the 9918A, and that VDP processor handles this memory, and it takes full care of this memory. It does memory refreshes. It accesses the memory for reads and writes, and so everything that we do with VDP RAM goes through a 1-byte window. We're not directly talking to VDP RAM. Through this window we talk to the VDP chip. The VDP chip in turn decides what to do. It passes the 1 byte back or forth whichever way we're going with it, or changes its registers according to the command that we've given it. Now, without memory expansion, let's look at VDP RAM without memory expansion plugged in. And even if you do, there's only a minor change. Basically, at the very top of VDP RAM, and this is for extended basic use, it changes around with editor assembler and basic do change this slightly, but basically, at the very top is where the screen is. Whatever you see on the screen is sitting here in RAM, and if you change a byte in the RAM area, it changes on the screen. This holds 768 bytes, 768 characters on the screen, 1 byte per character. The next one is what we call a Sprite attribute table. This is where, when you do a call Sprite in extended basic, this table holds the current Sprite location, its color, and its character, what they look like and what color they are. The next 120 bytes are reserved by TI for system use, and in there, mostly what's in this area first there's a sound list for when you do a call sound. Part of the sound list is put here and then passed out to the sound processor. So, which is interesting because it's put here. It comes through a 1-byte window, microprocessor handle. It goes back out a 1-byte window out to the sound processor. So a lot of 1-byte passing back and forth there. What else is in here is whenever you break a program, whenever you stop it with a function for, this area of memory holds a lot of information so that you can type in continue, and the program knows where to start from and continue on from there. So that's what this is used for very heavily, for when you type in continue. There's a lot of where to start and where things are in the program resides. The next section is what we call the pattern descriptor and sprite descriptor tables. And these hold, when you do a call char, that's where all of that information is thrown into right here. I don't know, you may have heard of that Extended Basic has an offset of hex 60 or 96 on its character code. So what's on the screen does not actually match the character number. It's been added to by hex 60. The reason for that is they overlap this table. This table actually starts up here at 0. But because of they did this to leave as much free memory area open as possible. So instead what they do, instead of having character number 32 at 32 times 8 bytes down, they added 96 more bytes to it, or 96 more characters to it, and so they just moved it that much further down, and that's why there's that offset in there that creates some havoc sometimes with the program. The next one is sprite motion. This just holds when you say, call motion for a sprite, put it into motion. This just holds the values, the X and Y values. That's all that's in this table. The next one is the color table. This holds all the colors for the different character sets when you do a call color. The following item is what's known as the crunch buffer. This crunch buffer is used when you are typing things in command mode, or when you just basically when you're typing things in, either in direct command mode or when you're typing in a program. So as you type them in, when you press enter, they're passed word by word to the crunch buffer, crunched down into that token code that you've probably heard about or read about. And once they've been crunched, then they're moved down into the program area and stored there if you're typing in a program. If it's not a program, if it's a command, after it's crunched, it's executed then. That's basically what the crunch buffer is used for. In Extended Basic, there's also an edit recall buffer. When you type something in, you have an error, you press function redo, and it comes back up on the screen again. It's sitting right here in GDP RAM in this edit recall buffer. The next item is the value stack, and this is, if you've been playing around with Forth, you're familiar with a stack. You push and pop things on and off the stack, and that's basically all that this area is used for, and it's used by some of the ROM routines for doing different things, v-add, v-subtract, that type of thing. The next section here is the program area, and in here is, as you type your program in, it's stored in here. Also what's stored in here is the line number table that points to where your different lines are in your program. Then there are the symbol table, or your variable names are all stored here, and they also point to where the string is. That, if you say a string equals hello, then it tells us here that a string is this, and it's this type of string. It points up here someplace, and this is where the word hello is, and that's what a string is. And then also in here is if you do an open statement, like open number 1, RS-232, your peripheral access block, or PAB as it's called, is up there. And that's basically nothing more than how the thing was opened up. Did you open it up as a display variable, AD, or internal, etc. And also what name that you used to open. So that's basically what a PAB consists of. And that's what's in this area. The last area here is the disk file buffer. And this area changes in size according to the call files. If you do a call files 1, then this area gets considerably smaller by 1,000 bytes, 1,036 bytes. If you do